We've been looking at different periodic trends. Let's look at trends in first ionization energy. We need this slide first. What is the ionization energy? We abbreviated IE. The ionization energy is the energy needed to remove an electron from an atom or an ion, and it's measured in the gas state. Ionization energy is always positive because you always have to put energy into the atom to get the electron off. Essentially, you're buying an electron from the atom. They're never going to pay you to take them, so you have to give them energy. So we can write a general equation for this. Some atom here plus an ionization energy will give us a positive 1 ion plus 1 electron. So this 1 electron has left the atom. IE1 is the first ionization energy. That's removing the first electron. Well, you can also take that positive 1 cation, add some more energy, and remove a second electron and get a plus 2 ion. That's called the second ionization energy. And likewise, there's a third and a fourth and a fifth, and you could just go on until you've removed all the electrons, but that's not usually very useful. So we talk about trends in the first ionization energy. So first ionization energy decreases as we go down a group. So if we look at the noble gases here, helium is at the top, xenon is at the bottom of the column. Helium has a higher ionization energy, xenon has a lower ionization energy. It's easier to remove an electron from xenon. And as with many things in chemistry, I correlate this to family life, and so the electrons are like children. And this is not politically correct, but aren't those things more fun? So here you have, this family has 2 children. We'll just talk about mom, because dad's off at work. So here's mom with 2 kids, and xenon has 54 electrons. So the circus has come down the street buying children. I've often said, it's a good thing the circus didn't come today because I would have sold 1 or 2 of you. Didn't really mean that. So for helium only has 2 electrons. You can imagine you're going to have to pay an awful lot to get 1 away. Xenon is practically going to give them away. Not actually, but you're going to have to pay a lot less for xenon to give up an electron. Okay? So why is that? Well, larger atom, those electrons are farther from the nucleus, so the force of attraction is less. I don't know where the selling children analogy came from. It used to be going to the fair. At a large family, this is why I don't take my children to the fair, because I don't actually want to lose them. The fair is a great place to have a child snatched from you, right? And if you're a small family here, helium has 2 arms and can hold on to the 2 electrons. Xenon would be like me with 6 kids at the fair, and there's no way you can keep hold of all of them, right? And so they're far away, and it's easier to snatch one. So it's easier to take an electron away from a larger atom. Going across a period, this is a general trend, but not an absolute trend. Generally, the first ionization energy increases as you go across. Again, because the atoms are getting smaller as you go across the period, and it's harder to take an electron from a small atom. The effective nuclear charge is increased, and so there's a greater force of attraction. So this is period 2, going across from lithium to neon. We see that the ionization energy increases. But there's a couple of zigzags in here. And in each of these periods, we see that there's a general trend with some little exceptions in there. Any questions so far? So the ionization is larger for smaller atoms. So these trends are exactly opposite of each other. Here's a cool graph showing different ionization energies, leaving out the transition metals because they're kind of weird. So we see going down a column, it's always decreasing. Going across, it's generally increasing, but there are some exceptions. So on the basis of periodic trends, determine the element in each pair with the higher ionization energy, if possible. So tin or iodine. So we need to look at these and find them on the periodic table. So there's tin, there's iodine. Where we're looking for the higher first ionization energy, is that going to be the bigger atom or the smaller atom? The smaller one, right? Because the smaller one, the electrons are tighter, it's harder to pull electrons off. You have to put in more energy. You have to pay the mom of a small family more money to sell her children. Yeah. Maybe we'll just let that one go away. So which of these is smaller, iodine or tin? I heard both. As we go across, they get smaller because the effective nuclear charge increases and the electrons get pulled in tighter. Iodine is smaller. The smaller one has the larger ionization energy. Here's another way to think of it, though. Does iodine form a positive ion or a negative ion? A negative ion, right? That's what it normally does. And it does that by gaining an electron. Do you think it's going to be real happy about losing an electron? No. What kind of an ion does tin make, positive or negative? Positive. So there are lots of compounds where tin has lost actually 2 or 4 electrons. So tin seems to be more okay with losing electrons. So this is higher ionization energy. It's another way to figure it out on an exam, right? Okay, calcium or strontium? There's calcium and strontium. Higher ionization energy, harder to pull off an electron. Calcium. It's the smaller atom, has the larger ionization energy. Carbon or phosphorus? Here's carbon, here's phosphorus. Well, the trend is that as you go across, they get larger, and as you go down, it gets smaller. So this is giving us 2 opposing trends. So you could say not possible. What if you're forced to guess? Because not possible isn't a choice on the multiple choice exam. Try this. Think about what kind of ions do these things make? Does phosphorus make a positive or negative? Negative, -3. So is it going to, you think it's going to be super happy about gaining electrons? No. What about carbon? Carbon doesn't really form ions. It doesn't lose electrons, doesn't gain them either. So I would put my money on carbon as having the higher ionization energy. Okay, fluorine or sulfur? We've got diagonal again, but diagonal the other way. There's fluorine, there's sulfur. Higher ionization energy. Which one's smaller? Fluorine. The smaller one has a larger ionization energy. You could memorize these things, but that never worked for me. I have to just kind of reason it out. Okay, so you kind of just have to learn the trend for atomic radius, but then ionization energy, you're pulling an electron off. If the electron is far from the nucleus, it's easier to pull off than if it's really close. So then you have to figure out, well, which one's bigger? It's easier to pull it off the bigger one. Or, would it be easier to steal one of Mrs. K's children or her friend who only has one child? It'd be easier to take one of mine, I might not notice for a while. Of course, 3 of them I've grown and flown, and so, they don't really count anymore. Okay, of course, exceptions, right? Exceptions to trends in the first ionization energy. So we just saw that the energy generally increases as we go left to right across the period. The exception is found between groups 2A and 3A. Boron has a smaller ionization energy than beryllium. So let's go back to that graph real quick. So here's beryllium and here's boron. We would expect boron to have a higher ionization energy, but it's actually a little bit lower. So let's see why that is. So boron is losing a 2p electron, whereas beryllium is losing a 2s electron. The 2p electron is at a higher energy level, so it's less stable and thus easier to remove. And then this says draw the orbital diagrams for boron and beryllium. So we've got 2s and 2p, 2s and 2p. And we'll say this is beryllium and this is boron. So beryllium has 2 valence electrons. We're just looking at the orbital diagram for the valence electrons. So 2 electrons would go in here. Boron has 3. 1, 2, 3. This sublevel is at a higher energy. And so removing this electron is easier than removing one of the 2s electrons. So boron's ionization energy is a little bit lower than beryllium, which is not what the trend predicts. Any questions? We see another exception between group 5A and group 6A. And so here we've got the orbital diagrams done for us. So nitrogen's in group 5A, oxygen is in 6A. We would predict that oxygen has a higher ionization energy, but it doesn't. It's lower than nitrogen's. So we see with nitrogen, it's got these s orbitals are full, and then the p sublevel is half full. Here we've got the s orbitals, again, full, and this p sublevel, this one has 2 electrons now, and then these 2 are half full. So the reason that oxygen's first ionization energy is smaller is we're removing this electron. That electron is having to pair up with another electron. Not super happy about that, and so it's easier to remove that one than removing one of these. These are at the same energy level. The other thing we see is what we saw with the irregular transition metals, where nitrogen has this nice symmetrical half-full subshell. When oxygen loses this 1 electron, it also has a half-full subshell. So we see this glitch between group 5A and group 6A. Now, when we look at first, second, third, fourth ionization energy, not comparing different atoms, but comparing different ionization energies for the same atom, we also see some patterns. So the removal of each electron subsequently requires more energy. So you take 1 electron, there's a cost. But now the atom's getting a little defensive. You want another electron, well, it's going to cost you more. And as you take more and more electrons, the price goes up. And sometimes it goes up dramatically. Much of this is because as you remove electrons, you get a higher effective nuclear charge on the remaining electrons. They get pulled in closer, and so then they're harder to remove. So for, let's look at sodium and magnesium. For sodium, its first ionization energy is 496 kilojoules per mole. The second ionization energy is almost 10 times higher. Well, there's a good reason for this. Sodium has one valence electron. So here we're taking the valence electron off. Okay, we got to pay for that. But now we're into the core electrons. The core electrons are much closer to the nucleus. Remember the trends with the ion sizes? When you make a cation, the cation is about half as large as the regular atom. So these are much closer. And so this ionization energy is really high. For magnesium, the first one is a little higher than for sodium. The second one is pretty big, but then the third one is huge. Well, what's going on there? Magnesium has 2 valence electrons. So you remove the first one, you remove the second one, it's going to cost more, but now you've taken off all the valence electrons, you're into the core electrons, and so the price goes way up. Any questions? So here's a table. Tables like this, you kind of have to look at them for a while before they make any sense at all. So what's going on here? Well, we just looked at sodium and magnesium. So first ionization energy, and we see the second ionization energy for sodium was much higher. For magnesium, it was the third ionization that was much higher. For aluminum, it's the fourth. Well, how many valence electrons does aluminum have? 3. So taking off the first 3, I mean, that's a lot of energy, but then it jumps way off. So the ionization energy increases as you take off valence electrons. Once you get all the valence electrons off, it jumps way up. Because then you're taking off core electrons, and that's going to be a lot more difficult. Any questions? This sort of stuff is not a huge deal in Chem 1A. You can pass the class just fine. It's not like stoichiometry or dimensional analysis or something. If you don't get that, you're sunk. This is, A student material. You better get this.